Thank you very much for your interest in my paper. In this presentation, I will provide all the results and also the intuitive arguments behind those results. And at several places, these arguments may not be very rigorous. So I will urge you to go through the paper to get all the details. This presentation is divided into 5 parts. The first part is what I call the prerequisites. Here I tell you about certain definitions as well as some theorems which are already well known in the mathematical literature. So as a reference, I've provided this excellent review article by Michel and Zielinski. So if you want to know more about these mathematical results, please go through this reference. So in this video, I will define certain concepts such as orbit of a point and stabilizer of a point with respect to some group G. And there's a theorem which states that under the action of a group, a manifold decomposes into disjoint strata. Then I will define a critical orbit. And then there is a theorem which says that the stationary points of a G-invariant potential form orbits under G. And also there is a theorem which says that points in a critical orbit under G are stationary points of every G-invariant potential. So to explain these definitions as well as these theorems, I would like to use a simple example. Let's start with a complex scalar field phi. So it has 2 components, real phi and imaginary phi, and our discrete group is the dihedral group D6. So it has 6 elements. The action of this group on a complex number is shown here. So first one is I, second one is bar, which is complex conjugation. Then you have rotation by 2 pi by 3, rotation by minus 2 pi by 3, then rotation by 2 pi by 3 after conjugation, and then rotation by minus 2 pi by 3 after conjugation. So these are the 6 group elements. Now I define an orbit. So orbit is defined for any point in this space. So you start with a point phi, and all points obtained by the action of this group on the point phi is the orbit of phi. So in general, you will have 6 points obtained by the action of d6 on phi. They are listed here. In this figure, I have given an example. If you start with point A, you get a total of 6 points given by A, B, C, D, E, F, which forms a 6-point orbit. It's not always the case that the orbit will have the same number of elements as the number of elements in the group. So that is demonstrated with another example. So you start with the point P in the x-axis, and then if you act the 6 group elements on P, you will not get 6 distinct points because complex conjugation on P is P itself. So ultimately you will get only 3 points, P, Q, R, and this is an example of an orbit with 3 distinct elements. And I'll show you another example. So this would be X, Y, Z. Then you also have the origin. Whatever group action on the origin is not going to change it, so the origin itself constitutes an orbit. Stabilizer of a point phi is the subgroup of G that keeps phi invariant. In physics, the terminology used is often residual symmetry group. In this work, I prefer to use the mathematics terminology, stabilizer. So as an example, I take the point P, and you can see that P is not going to change under the action of I as well as complex conjugation. I and complex conjugation form the stabilizer Z2 group. And here I call it Z2P. Two more examples are given here. The stabilizer of Q and the stabilizer of R. The stabilizer of Q is identity and rotation by minus 2 pi by 3 after conjugation. Similarly, the stabilizer of R consists of identity and rotation by 2 pi by 3 after conjugation. These are also Z2 groups, but they are different Z2 groups. So I name them Z2Q and Z2R. Now, if you look at the points X, Y, and Z, their stabilizers are also these Z2 groups. So the stabilizer of X is same as the stabilizer of P, which is Z2P, and so on. Stabilizers of points in an orbit form a conjugacy class of subgroups of G. Z2P, Z2Q, and Z2R form a conjugacy class of subgroups. Now, I define what is called a stratum. So, orbits whose conjugacy class of stabilizers are the same form a stratum. So, for example, the orbit PQR and the orbit XYZ, they belong to the same stratum because their conjugacy class of stabilizers is the same. Here in the figure, you can see 6 rays, and these 6 rays form one stratum. This stratum is composed of all orbits whose conjugacy class of stabilizers is that Z2P, Z2Q, Z2R. And we also have a second stratum, which is nothing but this green point at the origin. For this point, the stabilizer is the whole D6 group. The rest of the points in the plane that's shown with this blue region, that also forms a stratum. For any point in this region, the stabilizer is trivial. So we can make this statement. The manifold decomposes into a union of several disjoint strata. In this particular example, we have 3 disjoint strata. The green point, the red rays, and the rest of the blue region. An orbit which is isolated in its stratum is called a critical orbit. And from the figure, you can see that the only orbit which is isolated in its stratum is this green point. Now let me change the space on which the group acts. So you take any point on the plane and divide it by its norm. So then you get this unit circle. You can see that these red rays collapses to red points. And in this new space of this unit circle, these red points are isolated. You can see that there are 2 orbits which are isolated in the stratum now. One orbit would be these 3 red points, and the second orbit would be these 3 red points. Therefore, in the space of the unit circle, we have 2 critical orbits. Here I have constructed a potential using the field phi. This is the most general 8th order potential, and you can see that there are a total of 11 terms. These terms consist of an invariant part and a coefficient part, and so there are a total of 11 coefficients. So in this figure, you can see a contour plot of this potential. The coefficients that correspond to this particular figure is given here. So in this plot, you can see points. These points are stationary points, and I have given them colors based on where they are located. So you have a point at the center, that would be the green stratum, and there are points here on the red stratum, and also there are points outside, so that would be the blue stratum. Now if you change the coefficients, plot also changes. So there are several examples that are given. So in this particular case, there is only one stationary point at the origin. And there is one more example here. I have constructed these figures using Mathematica. The code is available online. The link is given in the description box. So you can manually change these 11 coefficients and see how the contour plot changes. So it's fun. What you can observe in these figures is that always stationary points form orbits. So blue points always appear as a set of 6. The red points appear as a set of 3. And of course, you also have a point at the origin. And now this is a very important theorem. The theorem states that points in a critical orbit under G are stationary points of every G-invariant potential. As we saw before, the origin forms a critical orbit. So what this theorem says is that if you have a critical orbit, then whatever potential that you write, the points in the critical orbit should form stationary points. And that is true in this example. In every case that you looked at, you have a stationary point at the origin. Now I am asking this question. What is the region in the coefficient space such that we always have stationary points in the red stratum? Why do I ask this question? Because that red stratum is the most interesting one for us. The origin, that's just 0, 0. That's not interesting. And the blue stratum, they are random points all over the plane. That stratum is also therefore not very interesting. But the red stratum has, as you can intuitively see, something to do with the symmetries of D6. That's the reason why I am asking this question. Let's first express this potential in r theta coordinates. And we have seen that if I change the space to a unit circle, then the red stratum becomes isolated. So it becomes 2 critical orbits. So that's what we are going to do. So we are going to remove the r dependence. If you have only the theta dependence, then you will always get stationary points at theta is equal to n pi by 3. It's a direct consequence of the theorem that I said before. In reality, you do have r dependence also. So I have to include it. In the radial direction also, you should have the stationary behavior. So that means the first order derivative with respect to r should also go to 0. So what we will do is that we will take a particular solution from theta, so theta equal to 0, and then get the potential as a function of just r, and then differentiate it with respect to r and equate it to 0. So that equation is given here. You may solve this equation and obtain r as a function of the coefficients c. You will have multiple solutions. For example, a solution with some number of real roots and some number of imaginary roots and so on. But the existence of a point in the red stratum implies that we should have a real positive root for r. Therefore, the values of the coefficients that leads to at least one real positive root for r will form the coefficient space that leads to stationary points in the red stratum. This completes our discussion of the prerequisites. In the next video, I will talk about constraints on the stationary points. I classify the constraints into intrinsic and extrinsic constraints.